Hello students, here are the answers to the worksheet that I put up at the end of the previous video notes. So here you can take a look and check your answers, make sure that you got the right answers. The first part here is figuring out center of mass, and the second part down here is figuring out the moment of inertia. Now, some students have complained a little bit about this particular worksheet. If we talk about rotation, right, if these masses, mass A, mass B, mass C, were rotating, and they were rotating in space, then really we should figure out the moment of inertia around the center of mass, because that's how it would rotate. It would, the center of mass would be the axis. But the way I asked the question here, I asked the question as saying that the rotation axis was right here at the origin. So whatever is making these things rotate, there's a hard axle, a strong axle right there to keep them moving around this axis of rotation. So yeah, it's a contrived problem, and I mean the point was just to get you guys to do to go through the steps. Okay, so let's get started with the next topic, which is going to be how to do conservation of energy problems, which now involve rotation. So the law of conservation of energy, it applies to rotation as well. Of course, it's the law. So let's take a look at how these sorts of problems work. And to do that, what I'm going to do is do a problem that does not involve rotation, but it does involve conservation of energy. And then after that, we'll do a problem that does involve rotation. And they're very similar problems, and so that it'll be easy to compare them. So here's my problem. I've got a mass, a block of ice. In other words, there's no friction in this problem, and it has an initial velocity, and it's going to slide up, get up to a certain height, and then after that it's going to slide back down, but we don't care about that. The question is, how high will it get? So what will h be? Okay, so to do this problem, this is how we approach it. We say that the energy at the final moment, which is when it gets to the top, has to equal the initial energy when it's down at the bottom. That's just conservation of energy. And then so now we break up the mechanical energy into its pieces, the kinetic energy part, the potential energy part, kinetic and potential energy parts. And then we put in formulas for each piece, 1/2 mv final squared. Now v final is 0, so this term will be 0. mgh for the final potential energy, 1/2 mv initial squared, and mgh, but over here, right, this is 0 height, so this term will also be 0. Notice that we have m, and m, so we can divide by m throughout, and the m's now go away. And so we're left with gh equals 1/2 v sub I squared, the initial velocity squared. Solving for h, dividing both sides by g, we have an answer. V initial squared equal over 2g will give us the height. Plugging in the numbers, doing the arithmetic, we get that it will go up 20.41 meters, a height of 20.41 meters. So that's how you do this conservation of energy problem without rotation. Now let's add rotation to the mix. Instead of a block of ice, we're going to have a basketball. And it's going to be going at 20 meters per second, and it's rolling. and it's going to go up the hill, it's going to stop, and once again the question is, how high will it get? And so we start out the same way. E initial equals E final. We split it up into kinetic and potential energy parts, and then get into the formulas. So we now have two different kinds of kinetic energy. This term here is the translational kinetic energy, and this is the rotational kinetic energy. And once again, we have potential energy. So, okay, now this side here, the left side is the final. So when it gets to the top, its velocity is 0. So that means that this term here is going to be 0. I'm going to cross it out. If it stops moving, it also stops rotating. So omega will be 0, so we don't need this term anymore. mgh is going to be its final potential energy. On the right-hand side, we have the initial conditions. It's moving along at velocity v sub I, and it's spinning at a rotation rate of omega, which we're going to need to figure out. And the formula for kinetic energy is 1/2 I omega squared, where I'll just remind you the I is playing a role similar to mass. It's the rotational inertia. And then as far as potential energy goes, it's going to be 0 because the height at the beginning is 0. Yeah, okay. So what I've done is I've made a copy here of the different moments of inertia for different shapes. So for example, let's say I have a hoop and it has radius r. Well, its moment of inertia will be its mass, which they call capital M, times its radius, which for whatever reason they call it capital R. Notice that it's a little different if you have a solid disk, right? This is a hollow hoop. This is a solid disk, and it's still mr squared, but there is a 1/2 in front of it. Here, this is an off-axis disk, and it looks like the factor in the front here is 3/2. This is like an airplane propeller, and for whatever reason, they decided to express it in terms of the overall length, and I'm having a hard time reading it. I think it's 1/12 ml squared. But I find it more useful to have it in terms of the distance from the axis of rotation to the end here, and I call that r. Anyway, there's lots of extra fluff here, but what we want is the basketball. So this is that basketball here, the hollow sphere. And the moment of inertia formula for that one is 2/3 times the mass times the radius of the basketball. Yeah. So we're going to use that. Okay. So, okay, now another thing that we need is, we don't yet know it, is what is the spinning rate? What's the rotational speed of the basketball? So to figure that out, you have to realize that when something is rolling, the ground is going past that object, and from the point of view, let's say you're moving with the basketball, right? As it spins, you're going to see the ground going past you, and the ground then has the tangential speed of like the bottom edge, the contact point of the basketball with the ground. So we use the tangential speed expression to work out what omega is. So it's right here. We have the tangential speed equals the rotational speed times the radius, and so we're going to solve for omega, which the rotation rate, and so we get that it's v sub I over r. So let's see, I think we can put everything together now. So we have let's see if we can do this here. Okay, so we've got the MGH, which comes out here. We have the 1/2 mv squared. All right, it comes down to here. And then we have the 1/2 I omega squared, and it comes down to here. But you see, the I is 2/3 mr squared, and so that's this right here. And the omega is v sub I over r. Okay, so that gets plugged into here, and it's omega squared. Okay, so we got that. And yeah, so we're making progress. It's messy, but we're making progress. All right. Now, at this point, we can divide it by m. And when we do that, all the m's go away like that. They all go away. And notice here, we've got r squared, and we're dividing by r squared. So the r's go away as well. Yeah, things are looking better now. Okay. And so I'm going to take all of this, and I'm going to divide by mg, and now we're left with 1/2 v sub I squared plus 1/3 v sub I squared. And here's the 1/2 v sub I squared here. 2/3 times 1/2 is 1/3. And yeah, now we need to add a half and a third. And believe it or not, I kind of mess this up sometimes, so I have to, okay, let's do it. 1/2 plus 1/3 is the same as 3/6 plus 2/6. It's 5/6. Yeah. Okay, so it's 5/6 v sub I squared. G's in the denominator. We plug in our numbers. Don't forget to square. And we get the answer, 34.01 meters. Now, isn't that higher than the block of ice? Let's go back up and see. The block of ice went up 20.41 meters. And the basketball, which is going at the same speed, is going up 34.01 meters. So the question is, why? I'm going to hide the answer. Why is that? Why does the basketball go higher than the block of ice? I mean, this would be the case if the two objects had exactly the same mass, right? They're going exactly the same speed. So why? All right, well, here we go. I've got a couple ways of explaining it. So one way to think about it is that the ice had just kinetic energy of translation. It was just going. The basketball had that same kinetic energy of translation, but it also had spin kinetic energy. And so that kinetic energy, that's an extra source of energy. And as it slows down, as the spin slows down, that energy is getting transferred into potential energy. And so it ends up going higher because it ends up with more potential energy. When the kinetic energy finally gets to zero, it's got that much more potential energy. So that's the energy way of thinking about it. Another way to think about it is that if something is spinning, you got to do something to stop it, right? To slow it down. Remember when I was doing the demo with the bicycle wheel, and I wanted to stop the wheel, it was spinning and rubbing, and I was going, ouch, 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 ouch. You know, it was doing work. It was damaging my hand. Not too much, but. So anyway, work is force times distance in terms of translation, or torque times rotation. And so as the ball was going down and slowing its spin, the reason the spin was slowing is that the ground was putting a torque on the ball. And from the point of view of the ball, you know, Newton's third law, the ball was pushing down on the hill, and so that force, which came from the torque, was helping push the ball further up the hill. We'll talk about torque next time. All right, so we're pretty much at the end here. Just a little point to finish up with. Notice that in the discussion, in the answer, the mass and the radius of the ball don't matter. And so mathematically, the radius, it matters in terms of the moment of inertia, but then somehow the r's cancel out, and in the end, it's not going to matter. And the similar thing with the mass. So it's really interesting that the mass and the radius of the ball don't matter. On the other hand, if you change the shape, in other words, if it was a solid sphere, let's say instead of a basketball, it was like a solid rubber ball, it wouldn't go up the hill quite so high. And if it was the hollow hoop, I think it would end up going up the hill a little further. Yeah. So that's kind of interesting. Okay, so that's it for this set of notes. Thank you very much.